Graphing first-order inequalities with one variable. Let's begin to explain how to graph the inequalities with the simplest type of inequalities, the first-order inequalities with one variable. We learned in tutorial 10.1 that we have four possible inequalities of this type. We have the following shown on screen. We have the following shown on screen, where a and b are numbers and x is the variable. Again, we will use the first-order equation with one variable. We have the following shown on screen. As a boundary line for the corresponding linear inequalities with one variable deriving from it, the four ones shown. From the previous tutorials, it is clear that the graph of a first-order equation with one variable represents a vertical line, as the graph concerns only the position of the coordinate x in a number line. Hence, when we represent graphically this type of equation on a xy coordinate system, it shows a vertical line because the y-coordinate does not matter. We have the following shown on screen. The graph shows the equation 4x minus 5 is equal to 0, where a equals 4 and b equals minus 5. From theory, we know that such equations have a general solution given by, we have the following shown on screen. In the specific case, this solution is equal to the following shown on screen. As shown in the graph. Now, let's explain what we obtain when the solutions of the four inequalities deriving from the previous equation are required. Thus, if we want to graph the inequality, we have the following shown on screen. First, we must isolate the variable x. Thus, taking the coefficient a as positive to avoid changes in the inequality sign yields, we have the following shown on screen. In our example, we have the following shown on screen. This means all solutions of this inequality extend to the right of the previous value, as shown in the figure shown on screen. In this way, it is obvious that the solution set of the inequality, we have the following shown on screen. Extends to the right of the vertical line, we have the following shown on screen. This solution set is shown by the colored zone that extends on the right of the line x equals 1.25. The dashed line shows that the value x equals 1.5 does not belong to the solution set of this inequality, as implied from the sign of the original inequality, which excludes the boundary value as a solution. Hence, we obtain the following rule for this type of inequality: in linear inequalities of the form a, x plus b greater than 0, the solution set represents all values to the right of the boundary value x equals minus b over a, without including it. If the original inequality, we have the following shown on screen. Instead, i.e. if the solution set, we obtain the following shown on screen. The solution set would also include the vertical line, the boundary line, that shows the equation 4x minus 5 is equal to 0, i.e. x equals 1.25. In this case, the boundary line is not dashed but solid. Instead, we obtain the following shown on screen. In this way, we reach the following conclusion about the linear inequality with one variable. We obtain the following shown on screen. In linear inequalities of the form a, x plus b greater than or equal to 0, the solution set represents all values to the right of the boundary value x equals minus b over a, including it. Now, let's see what happens if we have to solve graphically the linear inequality with one variable. We obtain the following shown on screen. The general solution for this inequality is, we obtain the following shown on screen. which includes all values on the left of the point, we obtain the following shown on screen. Without including it. Therefore, the boundary line x equals minus b over is dashed when shown graphically. For example, in the first-order inequality with one variable, we obtain the following shown on screen. The solution set includes all values that are smaller than 3.5, x smaller than 3.5. We obtain the following shown on screen. When shown graphically, this solution set includes all values on the left of x equals 3.5, and the corresponding boundary line is dashed, as the value 3.5 does not belong to the solution set of the original inequality. We obtain the following shown on screen. In this way, we obtain the following rule for such inequalities: in linear inequalities of the form a, x plus b smaller than 0, the solution set represents all values to the left of the boundary value x equals minus b over a, without including it. Last, if we have to solve graphically the linear inequality with one variable, we obtain the following shown on screen. The solution set contains all values on the left of the boundary value x equals minus b over a, including this one, as there is the combined inequality sign, less than or equal to, involved, which means the original inequality must be less than or equal to 0. For example, the solution set of the inequality, we obtain the following shown on screen. Includes all values from 3.5 to its left. Therefore the boundary value x equals 3.5 is shown by a solid vertical line when solving graphically this inequality. We obtain the following shown on screen. Hence, we obtain the following general rule for this case: in linear inequalities of the form a, x plus b smaller than or equal to 0, the solution set represents all values to the left of the boundary value x equals minus b over a, including it. Example: solve graphically the following inequalities and make the proof by taking one value of the variable from the solution set, and another value outside the solution set. A, 1 greater than minus 4x. B, minus 3x greater than or equal to 6. Solution. A. First, we must write this inequality in the standard form. We have the following shown on screen. For the graph of this last inequality, we have the following shown on screen. Indeed, if we continue to solve the inequality analytically, we have the following shown on screen. Now, let's pick one value from each interval, from the solution set and outside it, to confirm the correctness of our solution. Let's take for example x equals 3, which belongs to the solution set. Obviously, it must be a value that gives a true inequality. We have the following shown on screen. On the other hand, if we pick a number outside the solution set, for example, x equals minus 2, we have the following shown on screen. Hence, our solution is already confirmed as correct. B. Again, we write first the given inequality in the standard form. We have the following shown on screen. Let's make the coefficient a positive to avoid confusion. Thus, multiplying both sides by -1 yields, we have the following shown on screen. When this inequality is graphed, we have the following shown on screen. Thus, the part of the coordinate plane that lies on the left of the boundary line x equals -2, a line that derives from the solution of the inequality -3x greater than or equal to 6, represents the solution set of this inequality. The boundary line x equals -2 is also included in this solution set, as the original inequality symbol is greater than or equal to, which is a symbol that combines two other symbols in it. When the variable is not denoted by x but by y, the graph will be horizontal. All the rules are true except the orientation. Thus, if y greater than -b/a, the solution set includes the part about the graph without the graph line. If y smaller than -b/a, the solution set includes the part below the graph without the graph line. If y greater than or equal to -b/a, the solution set includes the part before the graph including the graph line as well. And if y smaller than or equal to -b/a, the solution set includes the part of the graph as well as the graph line. For example, the graph of the linear inequality with one variable. For y -12 greater than or equal to 0 includes the zone before the line y equals 3 and the line itself, as a equals 4 and b equals -12. Thus, since y greater than or equal to -b/a, we have y greater than or equal to -12, 4, i.e. y greater than or equal to 3, as shown in the figure. We have the following shown on screen. That is all for lesson 10.3.1. To continue this tutorial, please watch 10.3.2, Graphing First Order Inequalities with Two Variables. Thank you for watching. Make sure to like and subscribe to keep up to date with new videos. For more information, calculators, and tutorials, please visit www.icalculator.info.